Ok, tanto la telecamera sta andando.
So welcome, and today last two lectures for the course Interdisciplinary Studies on Internet. Well, after a lecture from Harvard professor, it is hard to say that this will be a lecture. Let's call it a public reflection on the topic on the scientific method in the era of big open data. I put open in parentheses because of the postulates that we have seen so far during the course regarding the openness of science. Okay, so first of all, some credits. Some of these slides come from works done with former colleagues at the University of Munich. Some other slides are borrowed from professors Paolo Sabini and Angelo Vulpiani, and I will tell you which slides. And this is how I'm going to structure the reflection, let's call it. I will give you an introduction to the problem. We will see some postulates to be on the same track. And then I will have a parse the students and a parse the students. So I saw there is one new on the. Can you please tell me which topic you are doing your PhD?
I'm a student, a PhD student in bioengineering and medical social science. It's an inter-university PhD with the Politecnico, Torino, and the University of Torino.
Okay.
I'm a pediatric surgeon, so it's a particular, it's interesting for me also because I deal with informatics and new technology.
Yes, and of course we can help us in the reflection. I asked because we polled the classroom yesterday in order to know what are the topics we are dealing with. So we will start from a fact. The impact of the internet on science has been huge. I wrote down just 3 examples. The first of all, there is a wide reach out of results thanks to the internet. The second point, there is, and this is a point which the European Union is stressing quite a lot, that is the potential engagement of new actors in the scientific process, where new actors are private companies, are citizens. We can hear in the European environment the term citizen science, that means including in the scientific process, scientific studies, the civil society as well. And the third point I mentioned, the large availability of data and techniques to analyze them. Techniques have become also not so difficult to use also for normal people. This is normal for people that, let's say, that is not does not belong to the university context. This is connected to the second point. Well, this is not a surprise because the internet was at the beginning a network that connected universities in the US. And what about the World Wide Web? Well, this is pretty the same, because this is an email from Tim Berners-Lee, the inventor of World Wide Web, and he wrote the www project merges the techniques of information retrieval and hypertext to make an easy but powerful global information system. The project started with the philosophy that much academic information should be freely available to anyone. And it aims to allow information sharing with international dispersed teams and the dissemination of information by support groups. So this was actually the goal of creating also the World Wide Web. So nothing surprising. As we have seen yesterday in the lecture of Professor Vedon, in in the last 3 years, this term open science has come on the hype. So we've seen yesterday, I won't repeat the limitations of such taxonomies. Actually, we see yesterday only this one from the Foster project. It was exploded. I took a more summary. And on the left, it's a similar one that is on the Wikipedia. The main idea that we should go back to open again the scientific process. I added digital science because this is because this is the wait, sorry, because it's much more comfortable for me. Oh, wonderful. We're speaking about digital, so this is actually, we are in the digital revolution. This is actually the big impact of digitalization in science. This is also a term that is used as a synonymous to open science, digital science, or open digital science. You will find also science 2.0. And from the philosophical point of view, we have seen yesterday that we should use the term free science. From the point of view of today, so all these terms are the same because we are reflecting on the impact of internet technologies and digitalization, massive digitalization to science. And the focus is on the third point of the three that I listed. So that is the large availability of data and technologies to analyze them. I will refer throughout all this reflection to an article that has appeared a few years ago, but there is still discussion on it. That has been issued in the Wired magazine. The end of theory, the data deluge makes the scientific method obsolete. How many of you already have read or have heard about this article? One? Okay. So this quote is useful. So this was one of the takeaway messages of the article that made a lot of discussion in the scientific community. The new availability of huge amounts of data, along with a statistical tool to crunch these numbers, offers a whole new way of understanding the world. Correlation supersedes causation, and science can advance even without current model, unified theories, or really any mechanistic explanation at all. So this was the message from the Wired magazine. Actually, it was not this message is spread throughout also the scientific community. So, for instance, I take another quote from a book, The Fourth Paradigm, Data-Intensive Scientific Discovery. In the 21st century, much of the vast volume of scientific data captured by new instruments on a 24/7 basis, along with information generated in the artificial world of computer models, is likely to reside forever in a live, substantially publicly accessible, curated state for the purpose of continued analysis. This analysis will result in the development of many new theories. So, is this true? Is this false? Is this partially true? So let's see how things are nowadays. This is an article that has been issued, I would say, a couple of weeks ago from Microsoft researchers. So what did these researchers have done? They analyzed queries on the Bing search engine to understand whether they could predict people who was affected by pancreatic tumor by looking back at their queries. So by having a set of queries looking on the cancer, pancreatic cancer, then they looked back in the past, they looked to what other queries these people, for what symptoms these people had searched, and so they drove correlations. And they claim that they were able to identify 5% to 15% of cases. So it's not extraordinary, but it's still a result for. So this research could be, this analysis could have been done by computer engineers that know nothing about cancer. The interesting thing is that the false positive rate was really low. So this technique, when it was signaling a case, was most of the time true. Another example from Facebook. This was already mentioned by Professor Brett Fisherman. Experiment with, again, a huge amount of data from Facebook. They were able to demonstrate that they could deviate somehow. Well, let's use the words of Frischmann to manipulate the feelings, the emotional state of people by changing the post on the visualization of the post on Facebook. This has been done with almost a bit more than 500,000 data points. Okay, so let's keep in mind this case because will be useful for later. I want now to, as I said, I want now to explicit some postulates to have all of us in the same track. Let's start from big data. So this is a quite common term, and I felt quite safe to take the definition from Wikipedia. But if you have another definition which is better suited, just let me know. So big data is a term for data sets that are so large or complex that traditional data processing applications are inadequate. So we need new techniques or more complex techniques than the traditional one. Still quite generic because what is traditional, what is not traditional. However, challenges include analysis, capture, data curation, search, sharing, and so on. The term often refers simply to the use of predictive analytics or certain other advanced methods to extract value from data and seldom to a particular size of data set. Do you know a better definition for big data? Have you ever encountered a threshold? Say, this is small data, this is medium data, this is big data. I didn't. So, I would, if you agree, one postulate is big data is large amount of data, where large depends on the context. Because if I am on certain types of social science where my normal sample is 5 to 10 people, having a sample of 200 people could be considered big data in that context, or 1,000 people. Probably in biology, 100 is a very low number. Anyway, this is an example of so-called big data. This is taken from the Wikipedia. This is a visualization from the edits, the daily edits in Wikipedia. Visualization done by IBM. And this is taken from a colleague of mine that he searched. I don't know. We will ask when he's back the original source. However, in the every day, 2.5 quintillion bytes of data are created. A quintillion is 10 power 30. It's a huge amount of data. And about 3/4 of this data is unstructured. So this is large data. Big data in science, one example. In your fields, you will have your own examples. At the Large Hadron Collider, protons collide some 1 billion times per second, and the CERN data center stores more than 30 petabytes. This is 1 million gigabytes, 30 bytes of data per year from the experiments. This is very large amount of data. that we have in science. So we have clarified among us the concept of big data. It's a large amount of data, where large depends on the context and the discipline that is studied. Now let's move to the scientific part. It's a bit more longer. Theory. I took this definition of theory. It is a framework to describe, explain, predict phenomena. We can put in and or in or, but these are the three goals of a theory. And it is a framework, can be a mathematical model, it can be a construct, a linguistic construct, an explanation, a written explanation. But if you all agree, we will take this as reference for theory. So it's a framework that has to describe, can explain, and can predict. Do you all agree with your studies? This is a good definition of theory? Okay. Let's go ahead with the postulate. So science, this is very hard to define science. We've seen, well, yesterday there some explanations on the methodological level, on the philosophical level as well by Professor Guedon. Was pretty clear. Here I stay on the method level, and this is a definition that came out after many seminars with my former colleagues. So we end up saying that science is systematically, objectively gaining and preserving, documenting and disseminating knowledge. And we know that the whole process, we know how much should be open for the good of science. And in principle, science tries to be objective. How? By aspiring to knowledge based on facts. However, so you all know that the accepting studies in certain journals, conference, or whatever is a social process. It is a mechanism, mainly based on peer review. So it has some subjectivity, it has some limitations. We've seen that in the current publishing model there are some biases, but some limitations. We could, for instance, take out some of these limitations by applying another model, so first publish and then filter. But in any case, this is a social process that is involved. And even with hard science, with mathematics, physics, logics, because in any case, well, there was a comment by Juan Carlos de Martin about Einstein. Well, even in the case of Einstein, the social process around was determinant, because at the beginning it was not easy to perceive the theories of Einstein. So, but with an extreme sentence, we can say, it's a bit extreme, but just to have clear the problem, that we could say at the end it is a matter of beliefs, capability, and the individual and social judgment. However, following some basic principle, rules, and codes. So, the takeaway message is that there is a process. In some young disciplines, the process is not, sometimes is not so clear. In the older disciplines, it is well established to understand phenomena, to gaining knowledge from nature, from people, from mechanism, to disseminating this knowledge. All this process tries to be best effort, as objectively as it can. However, it is based on a social process, and so it is subject to a certain degree of subjectivity, and this degree can depend on the field where you are working. Second postulate, let's keep in mind I'm not a philosopher, so I won't dive into this concept. However, science evolves too. At the beginning, the science in the Aristotle era had a certain meaning. Then it went through centuries. In the Renaissance, Francis Bacon is quite famous for his impact on science, saying that we advance in science when we advance in the knowledge of nature, and it was one of the main his main impact was to bring the inductive process. We'll see later what is induction in science. We had then the Enlightenment with the emancipation of science from the religion sphere, and then we had a huge impact by Kant and so on, until I would say that the modern science is based on the huge work made by Popper on falsifications, on falsifiable theories. And then here you have other important references in the last century. Another point: science and philosophy are interconnected, because we are speaking about knowledge, and the etymology of philosophy is a love of knowledge, right?
Yes, not exactly knowledge, but wisdom and knowledge in a large sense.
Let us know. I'm not a philosopher, so I won't be precise. And so here is just an example. We have a set of questions that come from ontology. Is there a world independently or subjectivity? Epistemology, how we gather knowledge, correct? And ethics. And we will see here, we will speak a little bit also about ethics in science. So, take away message: science is strictly connected to philosophy. And as Charles Nesson yesterday said, it is connected to the notion of truth. So here we are really at a very high philosophical level. And again, this is definitions by me and some former colleagues. We speak about truth with no subjective interpretation and distortion is possible. But still now I'm not so convinced about this notion of truth. In a scientific environment, we can say that whenever I repeat my treatment on a certain population, it will always lead to the same observation. So there is a certain degree of truth. However, is there such a thing like universal truth? That means how much my results are generalizable. Well, I'm a bit pessimistic on this. So for instance, I don't know whether we can reach in a lifetime, so let's imagine during a PhD. And what if my observations, analyses are dependent on human factors, on myself as an analyzer, or on the people who provide the data? I think that some, you in the bottom, you are working on the quantified self, right? Okay, so you are studying, you will study, so now you are collecting data from yourself, but in any case you will deal with people. So one important question is how human factors, human behaviors change when they know that you are collecting data. And assuming that you can collect data, we'll see later why. And so often things can be true only for certain contexts. And I love this picture because here we have the circle is represents the scope of the theory, the scope of validity of the theory. And here we know how the single studies combined together can enlarge the validity of the notion of truth. But still, we really don't know what is the real, the whole realm of a theory, what is truth. So it's a process. So by running multiple studies, hopefully independent, we try to verify the scope of a theory, to verify for which context a theory is valid. And so, summarizing and trying to close the postulates part, we work, again, this comes from a series of seminars I did in the past years, so don't take it, so it's quite reliable, but don't, of course it's subject to criticism. We work basically on 4 levels in science: on philosophical level, principal ways of working, methods and tools, and fundamental theories. We usually, during a PhD, from what experience we are most of the times here, but these reflections come from seminar to engineers, so probably in other disciplines we might touch all the layers or be focused on only a specific layer. And here an example, for instance, taking from a certain epistemological point of view, we use empirical methods to prove our theories, and we run experiments following a set of guidelines and using specific methods and tools to verify our hypothesis, whose confirmation or rejection rely on theory of statistics. So this is just an example. And then we have the scientific methods that we deal most with. They can be inductive or deductive. We can follow one way, the other way around, or both. Usually we have a study population. It is rare that we have all possible atoms under analysis. And then we do some observations and we try to build some patterns. We try to observe whether there are some patterns in the data, and then with an inductive process we build our hypothesis, on top of which, with several hypotheses, we form a theory. And then here comes actually the biggest heritage of Popper. The theory should have certain characteristics. First of all, should be falsifiable, verifiable, and then we set up, we formalize our hypothesis, most of the cases in a statistical form, so that we can run studies to confirm or reject them. Each scientific method has a specific purpose, deal with specific data types. Purposes can be, for instance, exploratory, descriptive, explanatory, improving in certain disciplines. And the data types can be qualitative or quantitative. Here an example with grounded theory. We deal with qualitative data gathered from a study population, and we build hypotheses that are descriptive, exploratory, or explanatory. Do you all know what is grounded theory? It's a method used in the social science where, starting from qualitative data from people, interviews, can be summaries, can be written text. There is a process of coding this text by one or more researchers, better or more. And then from the codes, from the labels, you build a second layer of concepts, and then you try to link these concepts together to form a theory. And then you need to, of course, to test the theory. So grounded theory is an example of inductive process. And here we have an example, some examples of other methods. You may have on your own fields, you may use some other methods. Where does big data? Well, with the definition, with the text that we've seen before, big data stays here. It was clearly stated with having a large amount of data here, we can go straight to theories. This was the main takeaway message. Finally, so what is the scientific method about? Actually, it's both about induction and deduction. It's a matter of hypothesizing, it's a matter of modeling and testing. That is forming some hypotheses, organizing them in a theory, and then test the theory to see if actually the data confirm it. And now we go back finally to our question. What about if we have a so huge amount of data, so large amount of data? If this method, if this scientific method is still valid, can we really get rid of the scientific method? Is it really true that correlation supersedes causation? I guess that you imagine my answer, but I think the answer is not so straightforward. It's not simply no. And I try to combine several perspectives now to try to decompose the problem, because it's a complex problem. Since I am an engineer, when I have to face a complex problem, I decompose it in pieces. And let's start with what I call a past and student. So in this part, I try to reject the hypothesis, say in scientific terms, that a huge amount of data is enough to understand the world and phenomena. So let's start from the limitations of statistics. That is, in most of the case, together with logic and of course mathematics, it is the theoretical framework is most used in a lot of disciplines. So I assume that most of you use things like p-value in your studies. Can you please raise your hands if you use p-value? Okay, my assumption was wrong.
What is p-value?
P-value is the probability, correct me if I'm wrong, probability that I reject an hypothesis. Well, in scientific hypothesis testing, I set up a null hypothesis and an alternative hypothesis. That is what really I want to prove. And so I accept the alternative hypothesis only when the statistics give me some evidence that I can reject the null hypothesis. I would say an example. Is it clear, or should I make an example? Null hypothesis can be after the Italian soccer team wins, people is more happy the day after. Well, actually, this is my alternative hypothesis because it's what I want to test. And the null hypothesis is the reverse. After Italian soccer team wins, people is sad or doesn't change nothing. And then I go to make some surveys. And of course, I can choose. I have to take care of some methodological aspects to make the experiment not biased. But then, with the statistics, I cannot confirm the null hypothesis. I have to accept the alternative one. Correct? Okay. Thank you. With a certain degree of certainty, that is the p-value. The p-value is the probability of rejecting the null hypothesis, given that was true. So it's the probability that my observation, what I observed from data, was actually a very extreme case. Do you confirm?
Must be inferior to 0.05.
Exactly. Well, this is a social convention. Could be 0.001, could be 0.10 if my research is really exploratory and or if I don't have a lot of data. But this is the rationale in any case. What do you use in your research? You don't use statistics at all? Who use statistics? Okay, good. And you may concur that with statistical tools we have some limitations, because we need, before applying a certain statistical tool, we need to check some assumptions. For instance, population data is distributed normally or not, and then I have to pick specific tools. Often we don't have enough data to draw proper conclusions, so we do not have a p-value that is less than 0.05, what we do? Can we really throw out our hypothesis? And, well, speaking about p-value in the last years, and speaking about limitations, one of the most used methods, so there is a lot of discussion in the community. So this is taken from a biomedical journal, showing up the limitation of p-values. Here there was even a statement of the American Statisticians Association to clarify when one should use p-value, when not, what is the limitation of p-value. And even we have in psychology the ban of p-values. So studies that use p-value are no longer accepted. You have to use other methods, or at least also other methods. You have to provide the raw data and so on. And now comes up big data again, hopefully. Big data gives an opportunity to given this limitation. I won't go, there is a presentation online by me where I present this technique that is control on false discovery rate rather on type 1 error that was p-value. So since you are not familiar with statistics, I will just say that the opportunity of having a lot of data gives also new methods and techniques to overcome the limitations of traditional statistics. And the paradigm that we have seen is you first collect the data, and then you ask questions later. Then you query the data, and you try what pop-ups, following a little bit of serendipity, using the terms, a term used by Charles yesterday. That translates an inference from data. Curiosity-driven research is also being called with big data. Data-driven research. So, by means of what? By means of regressions, patterns, observing with data mining, other techniques from historical data, basically. And then we often applied to prediction purposes. Because this is the most difficult part of a theory. Is not only describing, the next level is explaining, and the final level is predicting. If I'm able to predict what is going to happen tomorrow, the day, in 1 year, and so on, the theory is considered robust. Well, not so straightforward, again. I will show you 2 cases, and these are the cases that I borrowed from Professor Silos Labini, who is actually performing very interesting studies on relationship between economics, the economical crisis, and science. I really suggest you. And Professor Cecconi. They are both 2 physicians. So the slides I'm going to show you are not from my field. I will. Is anyone who deals every day with physics? For you, you are a mechanical engineer, right? So you will correct me if I say something wrong.
Oh.
Some others that are familiar with physics?
Yeah, I'm a mechanical engineer as well.
Okay. He was a spatial engineer. Okay, perfect. So please, if I say something wrong, just correct me. So, well, first case, deterministic approach. What does it mean deterministic? Is that if we know the mechanism behind phenomena, the laws of phenomena, we know for with a very high level of certainty that certain things will happen in a certain way, so that tomorrow will rain, that if I apply a certain force to an object, the object will break or not, and so on. It's also, I think that in physics, you have mechanics, you have a lot of these laws. Here a problem. The problem of chaos coming up mostly from Poincaré work. The problem is the following one. And it is that even if we know exactly the laws that govern the system, if the initial conditions are not exactly the same, our prediction can be totally wrong. So if we observe two trajectories like this one, that they start, we know very well the laws of these trajectories, of these functions, but they start almost the same point, but not exactly the same, then there are some other factors that may make our prediction totally wrong. Is right? Good. So let's go an example from physics. This is actually probably is also from, well, I don't know which phenomena in nature apply to this to a logistic map function. This is the form of a logistic map function. That is, the x at a time t plus 1 is equal to 4 times x at the previous point multiplied by 1 minus x, always at the previous point. It is proved that the prediction error doubles at every step. Every step that you go, you predict, you have a prediction error that is the double as the former one. In a deterministic, chaotic system, and again, deterministic is a system where we know exactly what are the mechanisms, the laws. We have that this error is proportional to a certain. So this is a constant e, and this is another constant. Is called Lyapunov exponent. It is greater than 0. So we know that is proportional to this exponent, and this exponent depends on the phenomena that we are studying. And this means, by resolving the derivative, that the time of prediction to stay within a certain error, delta, it is dependent again on lambda. What does it mean? That if lambda is very high, this time is very short. So we can predict within a certain error in a very short time. Then after this time, the prediction is very difficult to make. If lambda instead is quite low, instead the prediction window, as called, is pretty big. So it's easier to predict. Here an example with the same function and with two trajectories. You can see that at a certain point the trajectories diverge. And in this system, lambda was equal to logarithm of 2 and natural base 0.7. And we have the first phase of stability, high predictability. The second phase of chaos, low predictability. So what does it mean? That if we are not really able to measure with a high precision the initial state of our system, we may incur, after a certain time, huge errors. And this is an explanation why, for example, for tides, the ancient populations could predict pretty well how the tides were working. The Maya were quite advanced because this exponent was quite low, so the prediction window is higher. In the atmosphere, this is completely different. The lambda is, for reasons that I don't know because I'm not a physician, but the lambda is higher. The prediction window is if we want a certain precision, to contain our error, the prediction window is much shorter. So this is a first problem. This is my thesis. Even if we know all the laws of the system, even if we have a huge amount of data, that is not enough to predict successfully the phenomena under study. So big data, I say, is not enough. Depends on what we are studying. Second case. In the second case, we have a probabilistic approach. That means we really don't know what are the laws of our phenomena, but we have enough data, we believe we have enough data from the past, so that by observing the past we can infer what's going to happen. And with a certain degree of trust. And this is a probabilistic approach. So this is called the method of analogues. Given a certain point in the past, given at a present time, a certain point xm, we want to predict xm plus t in the future by looking back at a series of data that is called xk. So we check what happened to xk at time xk plus t. And we say that xm plus t is equal with a certain error, and this is the error, this circle, is equal xk plus t. So if the data in the past corresponds quite good with the situation that I have today, in the future will happen the same thing. If using the same example I did before with p-value, that means that if next Saturday, Conte will use the same players, we will win again. Are you gonna bet on this? Not so sure. Okay, this is an example. This shows how it is possible that the following steps, the actual prediction is wrong, is out of the circle, and this is the same example with more data sets. And here you have the whole process that I just explained. For further details here is very interesting publications. By the way, the slides are already on the website, and I will skip some slides. Of course, will be no object of the easy test tomorrow. But you have as reference. So considerations regarding this example. In an ergodic system, that is a system that after a certain amount of time goes back to its initial conditions, right? Correct me, eh? Almost right. So this time is inversely proportional to the probability of this is going to happen, that the same conditions are met. So what does it mean? That if certain conditions are very, it's very probable that they will appear again, the return time of the system to these conditions is very short. Again, we can say, using the same terminology of the deterministic case, that the predictability window is shorter. In such a system, this probability is the takeaway of this formula that I had some problems to fully understand. In any case, this probability is dependent, proportionally dependent, to the state vector, so to the number of variables that describe the phenomena. Right, okay. That means that if we need a lot of variables to well describe certain situations, so this probability is going to decrease a lot, and this time is going to increase a lot. So it's extremely rare that our system goes back to the initial conditions. That means that we are able to predict using the system of analogues, so looking at the back. So the good news that we have a somehow finite time. The bad news that depending on the precision that we want, for instance 5% precision, that in science might be even too high in certain fields, the minimum amount the minimum length of the series, that means can mean the amount of time to have a certain precision is quite large. So, some considerations. We have some systems, some phenomena such as earthquakes that are very, very complex to understand. There are so many variables that it's very rare to have to meet the exact conditions in the past. And also, we even don't know what are the variables sometimes, what are all the variables. And this was, for instance, the case of the failure of the Google flu algorithm. The Google flu algorithm was an algorithm that, very similarly to the case of Microsoft with pancreatic cancer that we've seen, that by looking at the queries of people, we were able to understand, to predict what was the peak of a certain of the flu. And so here is the reference to the article, and I will leave it to your curiosity. So here, okay. So there are some problems in saying that a large amount of data is enough to build theories, to predict phenomena, to understand even phenomena. We have seen two examples from in a deterministic case. We know very well exactly what are the laws of the system, and a probabilistic approach. So there are much more important questions to set up before collecting data. What are the relevant variables? What kind of laws regulates the systems? If there is any law, what kind of perspective we do take, deterministic, probabilistic? Are there any evolution laws? So they exist and are known, they exist and we have no clue. We even don't know whether the laws exist. So for instance here, this case, the case of the dark energy in the universe. We know it exists, we know it obeys to some laws, but we don't know all the laws. Here in traditional mechanics, I think that this is the first case. And here we know in human behavior, for instance, we really don't know. We are not sure that there are some laws. And so here are the common problems that we face with analytics. Not always the question or the problems are known. Even if you have a very large set of variables, can be not enough to well describe the phenomenon. Or even they can be too much. They can add complexity, unnecessary complexity, and so noise to our statistical analysis. And then we have the confounding factors. So other factors that we are not controlling for any reason, because it's too difficult, because we didn't think to control, that may have an impact on our studies. And then this is quite, this is a graph that I use a lot during my empirical studies. This is a graph that represents the types of validity for experiment design. How many of you are familiar with experiments? One, two, okay. I'll try to be quite general for all the class, so don't sue me if I say something not really precise. So when we build an experiment, we have a theory, a certain theory in mind, that a certain, let's call certain phenomena cause other phenomena. Well, I made example of Italian soccer team before. And then we experiment, if we have control, of course. We take a treatment, so we go down to the observation layer, to the data layer, in which we try in the experiment to reproduce what is happening, in our opinion, to the theory. So we inject a treatment to our system and we observe the outcome. And we need to have a control group, that means a group in which the treatment is not injected and we observe the outcome. We have another group in which the one or more treatments, according to several experiment design schemas, are injected and we observe the outcomes. if the two outcomes are different, we can say that the treatment had an effect. If not clear, I will repeat, in other words. Okay. So, what are the threats to validity? First one, conclusion validity. That is here, in this correlation. What we observe statistically, the outcome that we observe, is it really valid? So what is the probability that we are observing something by chance? What is the error involved? What is the measurement error involved in such a process? First type of validity. And I think that with big data, we are quite safe at this stage, because a lot of data in many fields correspond to very low probability of making an error, not in all fields. Well, the second validity is a bit more complex, and this is the internal validity. So, what we are observing, assuming that the statistics were right, that the outcome was really, so that we really observed a significant outcome, difference in outcomes in our experiment. Is the cause really the treatment that we injected, or some other factors that are interacting in our experiment that we cannot control or we didn't control? This is causation. And so, before saying that correlation supersedes causation, I would be a bit more cautious. So big data do not answer, do not cover do not assure this validity. Stops at correlation at the first one. So it's very useful, it's a very powerful tool, but it's not enough. We have to prove that there was a cause. And then we have to prove that the outcome really represents the theoretical effect that we are, that it's really representative for the theoretical effect. This is called the construct validity. And then we need to prove that external validity. That means that this is true for all the situations. That is, our observation in our experiment is generalizable. And these are just the four main types of validity for experiment designs. There are many other, and you will see, not in these presentations, but I can give you references if you need for your research. And so these are the types of validity explained. So this is my my assertion that this big data stops here. Very powerful, but still with the scientific method we need to assure all the other validities. And this is just an example for experimental design. Of course, for every scientific method we have other types of validity or other limitations to take care of. And then I like to conclude this, the parse destruence. Until what time is the
11.
11, okay, we'll finish earlier. This concludes the parse destruence. And I like to conclude with this quote from an epidemiologist. The root cause of our problem is a philosophy of scientific inference that is supported by the statistical methodology in dominant use. Again, the social process, again, the inference of big data. This philosophy might best be described as a form of naive inductivism, a belief that all scientists seeing the same data should come to the same conclusions. That is, still, we have interpretation on top of data, and on top of all the things that we have seen so far. And then I also suggest you to go to this interactive article. It's quite nice, interesting. There is a kind of test where you can see how results of experiments, of data analysis can change depending on the techniques, on the assumptions that you make. It's quite representative of the complexity of science. Any questions so far? Okay, now that no, actually I didn't finish the first part. I forgot about ethics. What about ethics? What about these studies that we've made at the beginning? What about informed consent? Did people know here, not here, on Facebook, that they were part of an experiment? Did Facebook collect consents? Probably yes. Probably when we signed yes, the terms and conditions, we agreed. But if this is really ethical behavior, what about here? When I use Bing, when I use Google, is it ethical that researchers at Google or Microsoft use our queries to make researches? So these are researchers published, researchers for the good. But remember what are the issues of social technical engineering, or the lecture from Brent Fishman? What is one of the main issues? Manipulation. What if these people is using our data to make research, to study how they can manipulate us? And this is a study that confirmed that it's something that is not impossible, at least. Well, in science, I said before, science is really coupled with philosophy and with ethics as well. There is a code of ethics for scientific studies. Many of them are defined by disciplines. So, for instance, in computer engineering and software engineering, I know the ACM standard of ethics. IEEE also has a standard of ethics. With medical and behavioral research in the United States, you have the so-called common rule that is inherited from the Declaration of Helsinki in the 70s, 75, I think. Every research in a public institution in the US had to go through an institutional review board. When I spent 1 year of my research in the US, I had to carry out a small experiment with human, and then we went through many days to think whether I should have asked the institutional review board permission or not. Then at the end we ended up no, because it was among colleagues, and somehow was fair enough to don't go through the institutional process. But there must be an approval by an ethical commission. And in these studies, there was no such a thing, because this is research environment carried on private companies. And this is one of the impacts that I showed you on the very first slide. The impact of digital technologies on science. One of the impacts was wider reach out and new actors that can make science. Today, private research is quite an important component of the research that we do today, without speaking about military research. And so this is a thing that we have to take into account when we speak about big data, even with big open data. Data comes from individuals most of the times, and we have to take care of the problems connected. Now we are in the parts constituents. So following this problem of ethics. So, as I said, big data is not the devil, of course, for scientific method. It's an opportunity. But there are many limitations and many problems to take into account. European Union is moving towards this. In the last December, a board was formed, Ethics Advisory Group for Data Protection. The president of the board actually is a trustee of Nexa Center, is Professor Luciano Floridi. Also, is well known as a philosopher of information. And so there is now the awareness, at least, of the institutions of the problem. We don't know the solution yet. So one big problem is algorithm accountability. It is a new research topic. How can we be sure that algorithms used also by private companies are fair, are ethical, and not used to make autonomous decisions, for instance, to give me a loan or not, to make me successful in an interview and get the job or not? How can we make even scientific algorithms accountable? And then here, I won't go, so here are a set of questions from a very interesting paper from the Council for Big Data Ethics and Society. And the paper is called Perspectives on Big Data Ethics and Society. And the paper ends with very interesting, important questions that we should really reflect upon. For instance, should human data science be regarded as human subject research? If yes, we have a set of ethical rules and a process to follow. Here, so the talk of the reflections of Brett Fishman were on the substantial part, the problem. Here I am on the process part. What are the quantifiable risks posed by correlative or predictive data research? Is there any risk that if an algorithm, when I'm searching something on Google, tells me, hey, maybe you are sick, you have a cancer. Maybe the algorithm is wrong, maybe I don't have a cancer at all. Or, I don't know, I do any purchase on the internet and there is Amazon that tells me, well, if you continue like this, I don't know, your stipend could be over by the end. I probably won't say something like this, but this is, I mean, you all buy on Amazon, we have predictive algorithms that tells us every time what we should buy next. And Google tells us what we should search next. This affects somehow our behaviors. These are just simple examples. And how? So we have spoken yesterday a lot about open data sets. So what kind of data should we really open? All data of the research? Really all? What are the risks associated to opening some data? Is it really true that we cannot have any more intimacy in research? So private, secret research? Or research that is so sensible that we need to wait a long time to be sure about the findings before it is public? And so before we put also all the data public? So I don't know the answer, and they also don't know, the authors of this paper. These are just questions. And so what are the benefits, the public benefits coming out from big data? How should we assure data privacy and security? What are the options for self-regulation on data science? And so on. I leave as a reference the slides. Now, let's go back to the method in my past construence. I've spoken about the methodological problems of big data, the big limits to the validity of studies carried on only using correlational analysis. How can I now, the question to be a bit more constructive is how can I support validity in my studies? Well, two possibilities usually. Support validity by construction, that means, and we'll see some examples, by controlling some of the threats, by trying to measure the effect of confounding factors, by blocking, measuring some variables, and so on. Or after the fact, after the experiment, that means by replication what's called reproducibility, or by making our study reproducible by other researchers that will test our data or our findings in an independent way. And this also increases the validity. If you remember the graph of truth, of validity of the theory that I showed you, this enlarge, if the other studies confirm our findings, enlarge the scope of validity of our theory, of our findings. And so here are some examples on how to support validity. So for instance, to improve conclusion validity, we should check all the statistical assumptions, also with big data analysis. What are the assumptions behind the techniques used, behind the statistical techniques? What is the probability of error that we are assuming when we are telling the world our findings? And are there any benchmark to refer to? Or the alternative validity is about causation. So by building our experiments or by building our surveys or whatever method you are using, we should minimize the side effects, or at least be aware and explicit them in a paper, publication, a talk. And the confounding factors, so factors that may influence the outcome of my experiment, or being unbiased with data. If you are testing a theory, it doesn't mean that the data will have to confirm our theory. And then other ways to improve validity of our studies. So one important thing is, even if you carry out an analysis using big data techniques, and even if this analysis has some limitations that we've seen, this is still of value, and we should check with other techniques that can go further in the hierarchy of validity that we have seen. So that triangulation, basically. And here I put an example on a study of myself with, in my sector was quite large data, 10,000 data points, and how I tried, what were the control strategies for all the threads that I analyzed. This is just an example. It's very, it's quite specific to the field of software engineering. It's not worth to go in details in this talk, but the takeaway message is analyze the threat, try to understand what type of threat I'm facing and what is my control strategy, if any is possible. And so you can say that, as I said, the most powerful tool is independent confirmation of our study. And so this is, again, going back to the concept so yesterday, this is the value of free science. Make other researchers make the work of the researcher easier in trying to test our theory, in trying to confirm or reject our theory. And this is a challenge. A PhD in Italy is time limited, is 3 years. So what is the degree of validity that we can reach? Well, I don't know. From my experience, the best is to try to get connections with the scientific community. And again, here is the social part of science. And to make the studies as replicable as possible, even if it will happen after the PhD thesis. And here is the point, is reproducibility of researchers. I don't know really, actually I'm not an expert of big data. I'm kind of expert of data analysis, of big data in my field, but I cannot say that I'm an expert on big data techniques. Also because we have seen that this definition is pretty fuzzy and it's really dependent on the context. But what I can see from my experience is that we should aim to reproducibility, not only replicability. So replicability avoids change. That means that is making other scientists making them in conditions to exactly rerun the analysis. So making all the data available, telling what tools we used, exactly what is the process that we followed, what techniques we use, making the codes of our scripts available, and so on. And reproducibility is much more. Is really in the sense of free science, well documenting everything. Ceteris paribus means the other confirmations will be treated at the same level as our studies, confirmations or rejections. This is a topic that is, in these days, in these years, really highly debated in the scientific community. There is an initiative of Nature started, I think, 1.5 years ago, and the journal proposed to have no space limitations of the method sections. So to give the authors all the necessary space to really well explain the method followed and make the research reproducible, not replicable. And having a pool of statisticians helping reviewing the papers and the measures before publication, and encouraging raw data online. And they even made an interesting checklist for scientists before sending a manuscript to Nature. And there are other initiatives that I put here as as a reference for your curiosity. So this is linked somehow to the impact of internet technologies on science, because as also we commented yesterday, there was a sharp amount of researchers in the last 20 years. Workers in scientific disciplines, private or public, are really much more than in the first 30 years after the Second World War. And so this means a proliferation of studies, and this means that if we don't make the studies reproducible, this is really a threat to finding reliable scientific theories. And then another point of view, infrastructure and norms. And if I well remember, is the last one. So big data, again, is an opportunity, but we need proper norms, not only ethical. We need policies, and we need an infrastructure. And what do I mean? So again, I recall the concept of open science, that is openness in all the aspects of science. About norms, I don't know if you know, how many of you work in a Horizon 2020 project? Oh, lucky you. So given that 2 years ago there was no funding for Italian fundings, last year there were 90 million of funding for research, so this is a very low amount of money. So if you will follow the research, the scientific career, you will have to face with European fundings, European projects. So to get your research paid, you need to win some project. If not, likely you. And so the funding program in 2008 was called FP7, and then it turns out, I don't know which year, 2010 maybe, you know when Horizon 2020 starts. Okay, nowadays we are under another funding period, okay, funding program. It's called Horizon 2020. So what does it mean? It means open access, making publication openly available. So there was during the FP7 program there was a suggestion by European Commission to make available all papers coming from an FP7 research program. Actually, I'm working right now on an FP7 program, so the FP7 projects are finishing in this year and next year, so it's still actual. And do you know about gold or green or so green means publishing our papers in a public institutional repository. For instance, in Politecnico we have Porto, University of Torino there is Aperto, and every university has its own institutional repository. There are some other repositories. There is a list of repository in the guidelines from Horizon 2020. For instance, Zenodo was mentioned yesterday. And there was a pilot, means from 2014 there was obligation. Every project in Horizon 2020 had to publish a paper in open access, regardless. So no matter was the publisher was sent the paper to. There was an obligation. Of course, there is some flexibility. It is a load and embargo period. That means that it is Elsevier requires 6 months. Usually it's 12 months for technical disciplines and 18 months for humanities, social sciences and humanities. But basically every journal has its own embargoes. By law in Italy, I think it's 12 and 18, if I will remember, or 6 and 12. I don't remember. But this is the order of magnitude of the embargo period. That means there is a period in which is allowed to have the publication closed, but then after this period expired, you have to open. You are obliged. And then, interesting, from 2017, from January 2017, in a few months, also open research data is mandatory by default. Every data that you produce, you collect during Horizon 2020 program has to be open. You have to use a repository. If your institutional repository doesn't give you the possibility to upload your data, such as Porto, for instance, you use some other repositories, such as Zenodo. And you see some more explanations on this resource. So this is a normative aspect that will affect the way we do science, and actually will give some opportunities to carry on some analysis with large data, at least for some disciplines. And there is this other initiative that is quite interesting. So it's the commission, the expert group met a few days ago to define the next steps. Is an European open science cloud to host publication data every product. I don't like product as a name. Every artifact coming from research. And well, let's see if I can show a short video, because this is quite interesting. I hope you can hear. Just to let you understand what is this infrastructure about.
Explained by the ZBW Leibniz Information Center for Economics. Amy is a biologist. Her current project on crab behavior of bees and echoes. Huge amounts of research data, such as measurements, already exist. Finding the relevant parts isn't easy. They're stored in different data centers all over Europe. For each of them,
course before, it will suggest me what to look first. Next. So what is about? Big words, big characters, as I put what I hope it will be about. So commons, data and resources that they belong to everybody. Commons on scientific data, of course. To be a bit less optimistic, we can say a federated environment for scientific data sharing and reuse. But this is the kind of infrastructure that we really need if we want to make really use of large data for our analysis, and a fair use. That means everybody can use it and make analysis to confirm or reject findings. And of course, access to this data should be made available to everyone in the world, not only European people. And this comes from a recent conference, from a project I'm working in, a Pasteur for Open Access. It's a research and policy project to promote and align the efforts towards open access to scientific publications and in Europe. And so, what's next towards this open European open science cloud? So it's difficult, as we've seen also from the video. It's a technical problem. It's a usability problem. We need to make the platform usable by everyone. It involves politics. It involves 800 universities in Europe, each one with its own standard and system, library system. And so there is an association of European universities that can be useful in such a process, and the process somehow has to deal with all stakeholders involved. It means also society, civil society. And there will be need of a technical infrastructure to connect all the data sets, or the database from the universities, because it will be a cloud, so not a physical silo, but a set of interoperating databases. And what is the governance of such an infrastructure? So this is a political matter, not technical. How can we make it sustainable? This is an economical problem. And so because we need, for instance, a support service for users, we need a larger database, a lot of space to store all this data and make it persistent. It means backup copies spread, physically spread, to make it resilient. And so the European Commission is working on this. It's not so easy, it's complex. How it is, as we've seen, the problem with big data in science is an opportunity, but it's not so easy as as we've seen the Wired magazine declared, as some books, some communities are telling. Here is a perspective. It's a slide from a colleague of mine, Giuseppe Futia, who is working on linked data. Linked data is a formalism to make data sets interoperable, to make connections between data sets. And this is already the state of the art. The data sets that are already connected in the internet. So the biggest one is DBpedia. DBpedia is the exact copy of Wikipedia written following the formalism, this formalism of linked data. It is a formalism where every data is described as a term, ternary composition, subject, object, relation. And so there is a whole scientific community that is working to promote, improve this formalism and the techniques, to develop pipelines to make use of the data in such a format, and to navigate, so to make the web navigable, queryable, to make things like where did the Rolling Stones played in 1980, to make such a query possible using a search engine. Now, if you write down on Google, on Bing, or whatever search engine, this query, you don't have a direct transfer. You have to go through the results and answer. And with such a technology, it is possible to get such answers. And if you think to the applications for scientific work, so this is quite an interesting opportunity. And so, since I am on the constructive part of my talk, these are the very last 2 slides, I mentioned you this symposium, big data and the human development. What are the opportunities given by big data for development studies, for studies that aim to improve life conditions in developing countries? So actually, you don't have to write a lot at least to get judged, and then you have a commission that decide whether your poster or talk or panel session is accepted or not. I just wanted to mention the constructive part is a good use of big data. But again, there is a research, there are new research field also on data ethics in this field. So making use of big data for the good, let's say, for developing countries, doesn't mean that we are allowed to take any data from these people. There are huge privacy violations right now on these countries. And I'd like to finish this reflection with a quote from Popper that I personally love, because I am an empiricist. Science does not rest upon a solid bedrock. The bold structure of its theory rises, as it were, above a swamp. It is like a building erected on piles, and the piles are driven down from above into the swamp, but not down to any natural or given base. And when we cease our attempts to drive our piles into a deeper layer, it is not because we have reached firm ground. We simply stop when we are satisfied that they are firm enough to carry the structure, at least for the time being. So I love this because somehow this quote is a bit frustrating somehow. That means I really didn't, after years of research, that means that I really didn't reach the truth. But at least for the time being, for certain conditions, with the help, with the collaboration of other researchers, at least some findings are able to hold the structure above. And until the next scientific revolution, as it was, for instance, the one brought by Einstein in physics. And okay, now here you have some, you will see on the slides some useful links and readings about big data and application to science, perspective from philosophy and ethics, perspectives from statistics, perspective from physics, plus the links that you have in your presentation. Okay, any comments? We still have 15 minutes. Question, critiques, suggestions. I mean, we could use this time or whether to prolong our break or to make a discussion. I mean, was clear enough? Do you think you will face big data in your research at a certain point? Have you ever read in your field, in your state of the art, that I think you did, studies done with large amount of data? No? well, in any case, I hope that this public reflection was useful, at least to rise up a little bit of the awareness and of a little bit also for building a critical awareness about the keywords. The keywords will, so before big data there was a sensor data was on the hype, and keywords in my field, for instance, are Internet of Things, and right now are what else? Ledger technologies in UK, blockchain is on the hype. So keywords come for central purposes, not always from scientific communities. There are economical interests behind keywords. That is why keywords change every 3-4 years. And before running behind those keywords, these trends, so it doesn't say that it's not good, because we need to publish, okay? So it's useful sometimes to use those keywords to label our research and maybe get a position on a talk or get a job offer and so on. But we really need to, as a scientist, we have the ethical, I think, not obligation, but how can, in Kantian terms, what were the commitment, exactly, the ethical commitment to reflect on what is behind the keywords. So what is behind the big data? We tried this morning to understand a bit more. It's larger data, okay. Some people need to call it big data, they will call it in another way in a few years, but let's try to understand what is behind, and then we can also use the term, but at least we are very conscious. Okay, so the next lecture is 11:30. Don't miss it, because it will be very interesting. By Bruce Sterling, thanks, and his wife Tetsanovic, and then Jasmina Tetsanovic, who they built an interesting house in Turin, Casa Jasmina. I think they will speak about it later. Any questions, just write me, and yeah, that's all.